Okay, imagine solving a problem that would take the fastest supercomputer on Earth millions of years, let's say, like 7 million years, and doing it in under 2 minutes.
Wow. That's hard to wrap your head around.
Sounds like something straight out of deep space science fiction, right? But what if the key to unlocking that kind of speed wasn't exotic, super-cooled machinery, but something you interact with every single day, something as simple and fundamental as light?
Intriguing. So light is the secret weapon here.
That mind-bending comparison is our starting point for this deep dive. We're peeling back the layers on a fascinating revolution happening in computing, the emergence of photonic quantum computing, and even leveraging photonics for AI, and how it could completely change how we think about computational power and, well, the infrastructure that delivers it.
Right, a whole new way of thinking about processing.
For this deep dive, we've looked at some compelling material, including sources highlighting a major quantum breakthrough powered by light, and a really interesting perspective on national strategies, and the players, vying for position in this rapidly evolving technological landscape.
Okay, so our mission today really is to give you the shortcut to understanding this shift. We want to unpack what makes computing with light so different, what recent achievements signal about its potential, and maybe see how different parts of the world are betting on this technology to lead the next waves of high-performance computing.
Let's jump in then. So where are we today?
Well, you've seen the AI revolution unfold, right? That's put incredible pressure on our current computing systems, demanding more and more power.
Yeah, we're pushing silicon chips pretty much to their limits, trying to keep up.
Exactly. The classical path of just shrinking transistors on silicon chips, which gave us those exponential leaps in performance for decades, that's really slowed down. Growth is much more incremental now, more linear.
And while we wait for probabilistic computing to maybe become mainstream, quantum computing is often seen as the path to break through those limits for certain kinds of problems. But some of the quantum approaches we hear a lot about face their own massive engineering challenges, don't they?
They absolutely do.
Yeah.
Take superconducting qubits, for instance, which some of the major tech companies are pursuing. Their biggest enemy is noise, thermal noise, vibrations. Even stray electromagnetic fields can just mess them up completely.
Right.
So to shield them, you need to cool them down to temperatures colder than deep space. We're talking millikelvin range. You
see the pictures, these huge, elaborate refrigeration systems, these dilution fridges built to house just a tiny chip.
Right. And if you imagine needing one of those enormous refrigerators for every few dozen quantum bits, scaling that up to the kind of numbers you'd need for a truly powerful quantum computer, let alone a quantum data center with millions of qubits, it becomes incredibly complex, maybe even impossible with current tech.
Yeah, building something smaller, even like a pocket-sized quantum device, seems like a huge hurdle with that kind of cooling requirement.
Exactly.
Okay, so that brings us to light. How does using photons change the game?
This is where photonic computing enters the picture. The core idea is basically to ditch electrons or trapped atoms and use particles of light photons as the fundamental building blocks for computation.
And what makes light such a good candidate? Why is it different from, say, electrons in a silicon chip or the superconducting qubits?
Well, the advantages of using photons are really compelling, and they tackle some of those big challenges we just mentioned. First off, photons are far less sensitive to heat. This is huge.
Okay.
It means a photonic system can run at room temperature, or at least very close to it. You dramatically reduce or even eliminate the need for that bulky, complex, cryogenic cooling infrastructure.
That's a fundamental difference right there. Less cooling means potentially smaller, simpler, and, I guess, easier to scale systems.
Exactly. Also, photons interact less with their environment compared to, say, superconducting qubits. They're just less prone to external noise, which helps maintain their quantum state longer, their coherence. But perhaps the most powerful advantage, and what the sources really highlight, is how naturally they lend themselves to networking.
Networking with light? You mean like connecting computers using light, like fiber optics?
Yes, but specifically for computing. If your computation is happening in the light domain, you can keep it there. You can send quantum information, like entanglement, between different systems using existing fiber optic cables.
So the same fiber that brings me internet could potentially link these quantum computers.
Precisely. This ability to naturally stay in the light domain means you can connect multiple photonic computing systems together relatively easily to build larger clusters or even massive computing centers. Think about replacing those huge AI data centers powered by GPUs with interconnected systems using light.
That's a big vision. Okay, let's look at a company that's been making significant strides in this area, Xanadu. The sources detail some of their work.
Right, Xanadu. They're a Canadian company focused on photonic quantum computing. And they recently announced a major achievement, performing a calculation called Gaussian boson sampling.
And that's the calculation that brings us back to our initial hook, the one that supposedly took a classical supercomputer 7 million years, but Xanadu's system solved in under 2 minutes.
Right. It's a powerful demonstration of quantum advantage for a specific type of problem. It shows that even with current photonic tech, you can tackle things fundamentally inaccessible to the most powerful classical machines we have today.
And their approach to building the quantum bit, the qubit, it's a bit different, isn't it?
It is. While a lot of quantum computing focuses on single particles, like a single trapped ion or a single superconducting circuit state, Xanadu's approach uses multiple photons to create their version of a qubit. They call these squeezed states.
That sounds counterintuitive. Doesn't using more stuff make it less quantum somehow?
You'd think so. But the sources explain that while a single photon is very quantum, using a specially prepared state of multiple photons, these squeezed states allows them to encode quantum information in a way that's actually quite robust and well-suited for certain types of calculations,
Yeah.
like that Gaussian boson sampling they performed, or maybe quantum chemistry simulations. Think of it less like just using more particles, and more like preparing the light itself in a highly complex quantum state that involves superpositions of different photon numbers, like 0, 2, 4 photons, and so on.
Okay, simplified explanation maybe. How does their machine actually compute using this light?
Think of their processor like a sophisticated light maze or an optical circuit, all integrated onto a chip. It starts with a laser generating light pulses. These pulses are then prepared into those special squeezed states.
Okay.
These pulses then travel through a series of optical components on the chip, like tiny structures that split and combine the light beams.
Like beam splitters, the things we sometimes hear about in quantum optics.
It's exactly beam splitters, phase shifters, things like that. As the light paths combine and interfere, the quantum properties of the photons interact with each other, creating complex entangled states across many light modes. The computation effectively happens as this light propagates and interferes through the maze. At the very end, they use highly sensitive detectors to precisely measure the light that comes out, essentially counting the photons in each output channel. The patterns they see in these measurements provide the solution to the problem.
So the interference and the final measurement are where the quantum computation really takes effect. That's where the answer comes from.
That's a good way to think about it, yeah. The complex quantum state is built up as the light travels and interacts, and the measurement reveals the outcome, which is probabilistic, by the way. You run it many times.
Got it. And they've built a new system to showcase this, the Aurora computer.
Yes. Aurora is their latest system. It links 4 photonic server racks together. And the key thing is how they link them just using standard fiber optics.
And the temperature. Is this the room temperature system we talked about earlier?
Primarily, yes.
Yeah.
The sources say about 90% of the system runs at room temperature. There are components that still require some cooling, specifically those high-performance photon detectors that do the final measurements. They need to be colder for maximum accuracy and low noise.
But not deep space cold.
No, nowhere near the extreme cryogenic temperatures needed for superconducting systems. It drastically simplifies the engineering compared to other quantum architectures. The Aurora system features 84 of their squeezed state qubits spread across those racks.
It's modular, scalable, and networked, running mostly at room temperature. That is a big deal.
Yeah, the sources highlight it as a world first in demonstrating a quantum computer that is modular, scalable, and networked in this way, operating predominantly at room temperature. It's a significant step towards building larger, practical quantum computers using photonics.
Let's dig a bit deeper into that networking advantage you mentioned. You said staying in the light domain makes linking systems easier. Can you explain that a bit more simply? What does that really mean in practice?
Absolutely. So imagine you have 2 quantum computers you want to connect, maybe in the same data center rack, maybe across the room. If they both use light for computation photons, you can simply send the quantum information, the photons carrying the quantum state, directly from one to the other using a fiber optic cable. The information stays in its native format.
Okay, like sending an email between 2 computers using the same operating system. Maybe a bit like that.
That's a decent analogy, yeah. Now, imagine trying to connect a quantum computer that uses trapped ions to one that uses superconducting circuits. They're completely different physical systems operating on totally different principles.
Right.
To send quantum information between them, you'd have to somehow convert the state from an ion's property, maybe its internal energy level, into a photon. Then you send the photon across a fiber, and then at the other end, you have to convert that photon state back into something the superconducting circuit understands, like its electrical state.
That sounds, yeah, really complicated and probably lossy.
It is. The sources describe this conversion process, this transduction, as very, very hard to do efficiently and without losing the fragile quantum information along the way. It's a major bottleneck for networking other types of qubits. By staying in the light domain from computation to communication, photonic systems essentially bypass this very difficult conversion step.
So the vision of linking many of these light-based systems via fiber optics to build those large quantum data centers seems much more achievable, at least from a fundamental physics standpoint, than maybe trying to do it with other methods.
That's the argument, yes. The natural compatibility with existing fiber optic infrastructure makes the path to building large, interconnected quantum computing clusters much clearer, much more direct for photonic systems.
Okay, fascinating. So we've looked at the scientific progress in engineering with companies like Xanadu, but the sources also broaden the perspective to national strategy. Germany, for instance, seems to be making a significant bet on IT and photonics overall.
They really are. The sources detail the new German government's massive investment offensive, a special fund totaling 500 billion euros dedicated to modernizing IT infrastructure, boosting AI capabilities, expanding networks, and also improving energy supply.
€500 billion, that's an enormous commitment.
It really shows the strategic importance they place on these areas. Goals include establishing Germany as a leading data center hub in Europe, dramatically accelerating fiber optic rollout across the country, something Germany has lagged on a bit, and digitizing government services.
Okay.
There's also a substantial increase in AI funding planned, aiming for at least €5 to €6 billion by 2025.
And they're talking about building high-performance computing centers and even an AI gigafactory with 100,000 GPUs. That sounds like a more traditional approach, maybe, to scaling AI power, like competing with the US and China on current tech.
It is, and that's certainly part of the strategy to strengthen Germany's innovation position using established technologies. But within this broader investment, the sources introduce a different, perhaps more disruptive perspective, particularly related to using photonics for AI computing today, not just for future quantum systems.
Oh, interesting. What's that perspective?
Well, it's the argument for significant investment in building the infrastructure, the factories, the fabs, specifically for photonic chips, and also in open source software development to utilize them effectively. The idea is that this could be a way to challenge the current dominance of GPU companies like NVIDIA and AMD in the massive AI computing market.
So seeing photonics not just for future quantum computers, but as a key technology for current and near future AI processing, kind of leapfrogging maybe?
Exactly. And Germany actually has a strong base for this. The sources point out that the German photonics industry is already large and vibrant, something like 1,000 companies generating about €54 billion in revenue in 2023. AI and semiconductors are identified as major drivers of this growth.
Okay, and a key German innovator mentioned here is QANT.
Yes, QANT is highlighted as a company pushing this vision, led by their CEO, Dr. Michael Furch. They are developing a photonic chip designed specifically as an accelerator for AI tasks, what they call an NPU, a neural processing unit, but based on light.
And this chip, the idea is it can plug into existing data center infrastructure, not a whole new system.
That's their design goal, yeah. It's intended to be a coprocessor that could be integrated into existing server systems, for instance, via a standard interface like PCIe, which is common in servers today.
Right.
This makes it potentially much easier for companies, data center operators, to adopt and upgrade their current infrastructure without needing a complete rip-and-replace overhaul.
That's smart. And they've also hit a notable milestone recently.
Yes. The sources mention that just this past February 2025, QANT opened the first pilot manufacturing line for their photonic chips at a facility called IMS Chips in Stuttgart. They invested about €14 million to get this line running. So moving from lab to production.
Okay. What's the core technology or material that makes their specific chip different? What's their secret sauce?
Their key innovation, according to the sources, is using a material called thin-film lithium niobate, or TFLN. The special property of this material is that it allows them to manipulate light signals on the chip incredibly fast. We're talking multi-gigahertz speeds, and crucially, without needing heat to switch or modulate the light.
Ah, okay, so it's an electro-optic effect, not thermo-optic.
Exactly. This leads to very precise control and, importantly, much higher energy efficiency compared to methods that rely on heating elements.
High precision and energy efficiency sounds pretty important for running large AI models these days.
Absolutely critical, yeah. Especially as models get bigger and data centers consume just enormous amounts of power. And this brings us to the performance claims QA&T is making, as cited in the sources.
Okay, lay them on us. What are they claiming?
They're claiming a significant energy saving up to 30 times more energy efficient for simple 8-bit multiplication compared to conventional electronic methods on, say, a GPU or CPU.
30 times, okay. That's already pretty good.
But then they project that for large language models, by combining this energy efficiency with the way their chips inherently handle the necessary mathematical operations, like matrix multiplications, their native processing server solution could offer a potential 90 times reduction in energy consumption and a 100 times increase in processing capacity or throughput.
Wait, hang on. 90 times less energy and 100 times more capacity for things like LLMs. Those are extraordinary numbers that could fundamentally alter the infrastructure and economics of training and running AI if they can deliver.
Yeah, if they achieve those numbers at scale, it would be absolutely transformative. Their vision is those native processing servers, NPS they call them, plugging in like easily exchangeable modules into existing data centers, working alongside traditional processors.
Making adoption simpler, as you said.
That's the goal. And their long-term ambition is pretty bold, for photonic processors to be a core pillar of global AI infrastructure by 2030.
Wow. The sources also give QA&T's perspective on why they see the limits of traditional silicon and electronics, prompting this shift, right?
Right. They point to the fundamental physical limits of using electrons in silicon, things like lower electron mobility compared to photons, the increasing challenge of managing heat dissipation as components get smaller and denser, the general slowdown of Moore's law we talked about earlier, and just the increasing difficulty in meeting the energy efficiency demands of today's most power-hungry applications like AI training.
So the move to photonics isn't just about chasing some theoretical quantum speedup. It's also seen as a pragmatic response to hitting physical roadblocks with the current electron-on-silicon paradigm, especially for AI.
Exactly. It's driven by the fundamental physics of trying to move and process information as fast and as efficiently as possible. And electrons are starting to look, well, a bit slow and power-hungry for some of these massive tasks.
Okay. We've covered the incredible potential and some real-world milestones here, both in quantum and AI acceleration. But what are the significant challenges still facing photonic quantum computing and, well, photonics in general for these applications? It can't all be smooth sailing.
No, definitely not. One of the main challenges highlighted in the sources, particularly for photonic quantum computing like Xanadu's approach, is something called optical loss.
Optical loss. You mean literally losing photons along the way?
Precisely. As light travels through the complex optical circuits on the chip, bouncing off mirrors, going through beam splitters, some photons can be absorbed by the materials or scattered out of the pathway. They just don't make it to the detector at the end.
And why is losing light such a problem? I mean, you lose data in classical systems too.
Right, but in a quantum system, losing a photon isn't just losing a bit of data. It can fundamentally change the quantum state you've carefully prepared. Too much loss causes the system to decohere, to lose its quantum properties and start behaving more like a classical, noisy system. You lose the very quantum advantage that allows you to perform those incredibly fast calculations.
So keeping the photons in the system, minimizing that loss, is critical to maintaining the quantumness needed for the speedup.
It's a huge focus for companies in this space, yeah. Reducing optical loss in the components and the overall circuits is essential for building larger, more powerful photonic quantum computers. And related to this is the broader challenge facing all quantum computing architectures, error correction.
Ah, error correction,
Yeah.
like correcting mistakes that happen during the calculation.
Yes, quantum states are incredibly fragile. They are easily disturbed by noise, by loss, by imperfections in the hardware, leading to errors in the computation. Building fault-tolerant quantum computers that can detect and correct these errors without destroying the quantum information is a massive research and engineering challenge.
And photonics has its own specific version of that problem.
Exactly. Photonic systems have their own ways errors manifest, like photon loss being a primary one, which makes designing effective error correction codes particularly tricky compared to, say, qubit-based systems where errors might look different. It's a hurdle the entire quantum industry is grappling with.
Okay, so we've gone from a calculation taking millions of years to under 2 minutes, explored computing with light, seen innovative companies in Canada and Germany pushing the boundaries, looked at massive national investment strategies, and touched on the hurdles like optical loss and error correction. What's the big picture takeaway for you from all this?
I think the core message, for me, is that the shift towards computing with light, in various forms both quantum and potentially classical AI acceleration, is very real and progressing rapidly. We're seeing demonstrations of incredible speed-ups for specific problems, yes, but also this promise of vastly improved energy efficiency for things like AI, which is a huge bottleneck today.
Right.
And maybe most fundamentally, a path to building interconnected computing systems that seems inherently more natural using light than trying to link other types of quantum or even classical processors.
And it's clearly a global race, isn't it? With companies like Xanadu pushing the pure quantum computing frontier with photons, while others like QANT, potentially supported by Germany's strategic investment, are making major bets on photonics as a disruptive technology for mainstream AI infrastructure right now.
It definitely brings to mind that famous quote from Richard Feynman, nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and it's a wonderful problem because it doesn't look so easy.
That quote feels incredibly relevant here. We're literally trying to harness the quantum nature of reality in this case, light, to build computers that can model or understand the world in ways classical machines just fundamentally can't. And as Feynman knew, translating that fundamental physics into practical, scalable engineering is anything but easy.
Absolutely.
But it leaves you with a big thought, doesn't it? If the fundamental layer of computing is indeed shifting, moving from manipulating electrons on silicon chips to controlling and measuring photons on integrated optical circuits, how will that change the very foundation of our digital world? What totally new applications, driven by this ability to compute and network using light, might emerge that we can't even envision today, much like Feynman hinted at the vastness and weirdness of the quantum realm? That's the really exciting and perhaps slightly mind-bending question to keep in mind as this technology develops.